All right, now in this video, we're going to broaden our understanding of logarithmic statements. So the goal of this is that you can take a logarithmic expression, enter it into a graphing calculator, and or a scientific calculator, Desmos, and that you can interpret the number that it gives you, the output that it gives you. So that you, once again, don't seek to just get work done, but seek to learn. Okay, so here we go. All right, so the first example that I've provided for you is log base 7 of 1/49th, okay? And Desmos tells you that is -2, all right? Now, you need to interpret that by saying, well, I know that 7 to the -2nd power is 1/49th. In other words, what logarithms really solve for, logarithms really solve for exponents. All right, so you can think of that -2 as an exponent. That's really what logs do. And you can see right here from the visual that we had in the first video, right? The output of the logarithm is the exponent of the exponential expression. All right, so you're finding missing exponents. That is really the whole deal, right? When I have a missing exponent, I don't know what it is, I use a logarithm. Okay. How about another one? So how about log base 3 of 3? Okay, log base 3 of 3, that reduces to 1. And you can think of that because 3 to the first power equals 3. All right, you can also think of it as log base 3 over 3. It's like they cancel out. You're just left with 1. Okay, log base 4 of 1/4. All right, it's equal to -1 because 4 to the -1st power is 1/4. All right, you can also think of it as, well, the common base right here for 4 and 1/4 is 4. So 4 to the -1 power. Think of the log base 4 and the 4 canceling out. You're just left with a -1. All right, so that is how you make sense of logarithmic statements in a moderate view. Okay, here's some more complex ones. So log base 125, that's a huge base. Log base 125 of 5, well, that's equal to 1/3. All right, reason being 125 to the 1/3 power is 5. Remember, the 1/3 power really means the cube root. Okay, and why does all this help us? Well, really, the purpose for this, the purpose behind understanding logarithms is to reinterpret exponents, right? We understand exponents and we understand logarithms. So we never really get by understanding a logarithmic statement without going back to the exponential statement. All right, so check this out. Here's how it'll come in handy for your practice. All right, so if I have a function 7 to the x divided by 5 minus 10, okay? So let's say that's your function and you want to find its inverse. Well, we already know the steps for finding inverses, apparently, right? So we are going to say, okay, so switch your x's and y's, piece of cake. Inverse operations, add 10, multiply by 5 to both sides. So far, so good. But then look where you are now. Oh, sorry, you're at this point. 5x plus 50 equals 7 to the y. All right, so 5x plus 50 equals 7 to y. Let me write it right here, and let me remind you that this is an exponential statement. 7 to the y equals 5x plus 50. All right, this is in the same format. 7 is my b value, right? Y is my a value, and the expression 5x plus 50 is my n value. All right, so I can turn this into a logarithmic statement. So I need to say log base 7, all right, you see the base is b, all right, of 5x plus 50 equals y. And now you have found the inverse function. So see, that wasn't that bad. Because I understand logarithms as inverses of exponents, I can now invert exponential functions, all right, which we were not able to do. It's the whole reason why we learned inverses, to invert exponential expressions, okay? Cool. Let's look at one more example, all right? One last example right here, all right, in the 24 seconds that we have left, all right? What if we have a base e, all right? Take a look at the steps that I followed right here. I switched x's and y's, I inverted the operations, and I ended up with a statement that said x minus 2 over 3 plus 8 equals e to the y. All I have to do is invert that, but I invert it not just with a regular log, but with